Welcome to this lecture where we're going to talk about how to maintain AVL balance. The purpose of this lecture is to talk about the general approach of maintaining balance, and we're going to talk about how we keep track of which path we should look at in order to determine whether an imbalance occurs and fix that imbalance. And we'll talk about some special cases on remove. So the general idea behind AVL trees, AVL balance trees, is to keep them balanced at all times. Keep them balanced at all times. But the problem is that inserting and removing can cause imbalance. It doesn't always, but it could, and so we need to fix that as soon as it occurs. So when we do an insert or a remove, we do the entirety of that insertion or removal. And then after that, we fix anything that has gone wrong. So that means we have to look at the heights and update them along the path that is involved for that insert or removal. We have to detect and fix any imbalances, and we have to do all this without slowing down the tree. In other words, we want our insert, remove, and search to remain log n performance, so we don't want these fixes for rebalancing the tree to slow that down at all. And so here's the basic idea. Okay, this is the heart of this lecture on this one slide. Inserting and removing, as we've talked about before, can change the heights of various nodes in the tree, but it can only change the heights of nodes along the access path. Okay, so if we had a tree without this node, and then we were to insert 5, all of these nodes have their heights updated, possibly. But none of these nodes could have had their heights updated because the 5 didn't impact that node or that path at all. Okay, so if you have a gigantic tree, only the nodes along the access path for your insert or remove can be affected in terms of their heights. And so what we have to do is keep track of the path as we're going down. So if we're going to insert 5, we keep track of the path, and that would be 40, 20, 10, and then 5. And we could keep that as sort of a stack, right? And the stack is pushed on 40, 20, 10, 5. So if we pop off the stack, we're going back up the tree. 5, 10, 20, 40. So we're going back up this direction. And as we go up that direction, we travel back up the path and we update the heights. So we can update the height. This height was, before we did this insertion, this height was 0, this height was 1, this height was 2. And after we do the insertion of this node, then this height becomes 0, this height becomes 1, this height becomes 2. And at the point where we discovered this height is 2, we see that there's an imbalance between this node with height 1 and this node, null node, with height -1. Okay, so we travel back up the path, we discover right here that there's an imbalance, and we go to fix that imbalance immediately. Okay, so again, as we go to insert, we travel down and we maintain this path. We build this path as a sort of a stack. And then to go back, we do the insertion. So the insertion goes there and there in the tree. And we travel back this way by popping off the stack. And as we go, we update each node's height and detect imbalance and fix via rotations. Okay. If instead of doing an insertion, we were doing a removal, and say we were removing this node, okay, 50, the path for that removal would be 40 to 60 to 50. But since 50 is being removed, then the path is just 40 to 60, and we would have to travel backwards up this path towards the root and update the heights of 40 and 60, okay, or possibly update their heights. Check that whether they need to be updated, and check for imbalance. So at a high level, this is the idea. Whenever you do an insert or remove, you build this path, which you can think of as a stack, going down the tree, and then to get back up that path, you just pop up that path, all the nodes that you encountered, in order to update their heights and look for imbalance, and fix them as you see them. Now, there is a special case, and the special case is if you want to remove a node that has 2 children, because you need to look at all of the nodes that might have changed. So the update path that we're talking about has to consider all nodes whose heights may have changed. And that means that if we're removing 120 in this tree, 120, you might think that the path only includes 80 and 120, but that's not true. Because in order to replace 120, we had to go to, just like with a regular BST, we had to go to its right subtree and go to its leftmost child, which is 130. So if we're removing 120, 130 gets sort of put into its place, which means it gets plucked out of this subtree, which means that the heights of everything that are possibly affected are 140, 160, the replacement for 120, which is 130, and 80. Okay, so that's what I've drawn here. After we remove 120, the path that we need to update actually is 140 down here, 160 here, 130 here. Notice that 130 is replacing that, and then 80. Okay, where did 120 go? Well, it was removed, right? And taking the place of 120 is 130. So it's important to notice where 130 ended up. We don't want to update the height of 130 down here first, right? Because it has a height, it needs its height to be based on this node, which needs its height to be based on this node. So we have to update the heights bottom to top, since each height depends on its children. So the order in which we process this path matters, and the position that we put 130 into this stack or this path also matters a great deal. Okay, so just keep that in mind when you're removing a node that has two children. Otherwise, you're building the path identically. And let me just give you a comment on how you might build this path as you go down. So suppose I'm removing 120. What I do is I travel 80 and then 120, and I find the node that I'm looking for. So as I'm building this path, I might create just a blank entry right here. And when I say 80 here, of course, that's just a pointer right to that node. And when I create a blank node here, this could be a null node, okay, or a null pointer rather. And then I have to continue down. So I'm going to have 160. So I'll put that here. And really that's a pointer to 160, 140. And then I have found the leftmost child. I don't put 130 here, right? I don't want it there. It needs to be where it's going to belong after the update occurs. So the 130 is going to be at this null pointer, which I saved maybe an index to, so that I can then go backwards up this path, starting at 140, which is the appropriate starting place, and going back up towards 80 and having 130 in the proper order. Okay, so this is the idea for how you travel back up the path and update heights, detect imbalances, and fix those imbalances.